Good. So let's start. So let's have Professor Polzik second lecture. Thank you.
All right. So special thanks to those who were partying yesterday by my windows at 3 in the morning. If any of you are here, you're very welcome. So we continue from where we finished yesterday, and just remind you that we were talking about the quantum interface between light, photons, and collective spin degrees of freedom of atoms. And I again emphasize that I call the atomic degrees of freedom spin degrees of freedom, but this is sort of a generic name in my vocabulary for spin 1/2. So it's essentially, doesn't have to be spin. So let's look at the equation that we saw last time, and if we want to make a nice measurement, and nice meaning the measurement sensitive to the quantum features of my atomic ensemble, for instance, then I have to measure a certain quadrature of light, and it will consist of the intrinsic noise of light. If light is in a coherent state, like a good laser, then it's just short noise, and the signature of the atoms. And the whole point is that the signature of the atoms, the quantum noise of the atoms, should be mapped on light, and the coefficient here is this kappa. This should be large. In fact, because this is normalized to 1 and this is normalized to 1, roughly speaking, in the canonical variables, then it just has to be much greater than 1. And if we look at this coefficient, it looks a little scary, but in fact, what we see here, I actually, by the way, would be happy to provide copies of my lectures, whoever is interested. So we will have here the absorption coefficient, or the optical depth of the ensemble, and the detuning of interest, the saturation parameter, the detuning square over the natural line width, and so on. And the way it's written here, it just helps you to understand that if you do some simple transformations, then this figure of merit will be the product of the optical depth on resonance. So most of our measurements are done off resonance, but this is the optical depth on resonance times the probability of spontaneous emission. And spontaneous emission is something which is not so good for the interface, and I'll show you in a minute why. So this is the generic level structure. So we have atoms in the beginning all in one of the substates of the lower state, and as a result of this quantum interaction, so this is classical fields, those are quantum fields. As a result of the interaction, we're generating some interesting excitation here, and together those two form the quantum state of interest. And the thing is that, this is just rewriting this equation, reminding you that in fact in this setting, this normalized atomic variable is just the difference between the two populations here, normalized to the square root of n. And this is it's not a problem, it's a feature. So remind you that we're sending light through the atomic ensemble, and then we're measuring on the transmitted light. And we make a measurement which is either a phase shift or polarization rotation, something nice. But again, if you recall your basic atomic physics course, you will remember that no phase shift happens without spontaneous emission. So the phase shift and spontaneous emission are the imaginary and real parts of the complex polarizability. And so you make a measurement here, which is a useful measurement, and at the same time you inevitably cause spontaneous emission, and this is what it looks like. And the big difference between the spontaneous emission, which is those dashed lines, and the quantum field, is that the quantum field is forward scattered. It's a collective effect. Whereas those guys, they are individual atomic effects. And so this spontaneous emission is the process without phase memory, and essentially it just dephases your quantum state of interest. Because, you know, if you have spontaneous emission like that, then the state of this atom has no connection in terms of phase to the initial state. So this is why spontaneous emission is just a dephasing process, but as we see from this simple equation, no spontaneous emission, no quantum interaction. So this is again and again to re-emphasize that the optical depth of resonance is your figure of merit. Compare it again to the quantum electrodynamics that people know and love, where you have atoms in an optical resonator, and then you can have a few atoms. If the finesse of this optical resonator is large, then you will have large effective optical depth, so to say. And in this case, we don't have a cavity, but we have so many atoms that this quantum comparativity is large. Okay? So this is just what I said, that the probe depumping parameter theta, should be small, because if it's large, then it wipes off all interesting quantum states. And that means that if we want to have a good interaction, we need large optical depth. And this is just another way to write it down. This alpha naught times eta. You can rewrite it, and you will see that it's actually proportional to the rate of spontaneous photon scattering. Okay, so let's revisit the measurement process once again. And we looked at it last time. Let's just continue. So we have a driving field, coherent field, shown here with solid lines. And we have a quantum field coming in. And I put in quantum field in the orthogonal polarization to the classical field, so that the quantum field is expressed here with those dashed lines. And indeed, those polarizations should be orthogonal to those two if we have the delta M Zeeman levels non-degenerate. And again, this field can be in a vacuum state, or it can be an interesting quantum field that you want, for example, to map on the atomic state. So this combined mode goes into the polarizing beam splitter, and it will be measured. But if we want to make an interaction with atoms, then we put atoms here. And what happens is the following. If this is the initial collective spin of those atoms, and I send light through, then if my atoms have quantum fluctuation of the spin, which makes it, you see, this is meant to be exactly orthogonal to the direction of light propagation. And if it's orthogonal, there is no polarization rotation, because polarization rotation is proportional to the projection of the spin on the direction of propagation of light. But there is always some non-zero projection, because this field, this spin, has quantum fluctuations, as we discussed. And those quantum fluctuations, which are random, small but finite, they will cause rotation of this polarization, as we discussed last time. So that's how it is written in canonical variables. So you have light, it goes through, and the P of atoms is exactly this quantum projection of the collective spin on the direction of propagation. And you measure it. And you can write it in more kind of human units, in a sense that the measurement that you perform is described by the Stokes parameter, which is polarization rotation. And this is the shot noise, and this is the rotation proportional to the projection of the spin in direction of propagation of light, and off we go. So how does this work, for example, in a atomic magnetometer? So we have light polarized like that. We have the atoms which are placed in the bias magnetic field, and therefore the spin is oscillating around this field. What is oscillating here, in the absence of any other fields, are the quantum projections of this spin on the orthogonal direction, as we discussed last time. Even if I tell you that classically the spin is oriented like that, there will always be quantum fluctuations, and they will be oscillating, and that's nice, because we want to make a measurement at the frequency which is non-zero. Quantum measurements are better in this way. So how do we use this for magnetometry? Suppose we want to measure an AC magnetic field, the oscillating magnetic field. Then we have to choose the Zeeman frequency of the DC field equal to the frequency of the AC field. Then you have like a resonant condition. This spin is oscillating with a certain Zeeman frequency defined by this B. And now I add the field of interest that I want to measure in the orthogonal direction, which is oscillating at this same Laurel frequency. And now you have a resonance, because you have a spin oscillating, and you add oscillating force, and life is good, and then you can measure this oscillating magnetic field. And if you want to measure the oscillating field at another frequency, you just choose the different bias field. So again, the good news here is that we're making measurements at a certain frequency, which means that we're only sensitive to the noise around this frequency. And this helps to choose the frequency in such a way that you suppress all classical noise sources exactly around this frequency. The lower this frequency is, the more difficult is your experiment. Okay, so a little bit more equations. We have the oscillating projections of the spin. So they're oscillating like that. Here's the frequency oscillation. They are pi over 2 out of phase, right? Because this is Jz and Jy. And the oscillation amplitude is proportional to the length of the network, of course. And it's also measured by the input light quadrature operator. So you measure this frequency of oscillation. What is shown here is that because the spin projection on the z-axis is oscillating, the polarization is also oscillating, and this is what you measure. So the result of this measurement is, again, in Stokes parameters, shot noise, the back action of light, the projection noise of your atoms, and the signal. And in this particular incarnation, the best you can do is to find a good balance between the back action of light on those atoms and the signal. And it turns out that if your measurement is very weak, then you are mostly limited by the shot noise of the probe. And the signal is small. If your measurement is stronger, in a sense that your coupling coefficient is between atoms and light is large, then you are totally dominated by the back action of light. And if you choose the interaction strength in the right way, in which case you just decide how long your measurement lasts or how strong your light is, then you have this golden balance which you can only overcome with some kind of entanglement. So it's a very general statement. If you have a system that you want to probe, it's a quantum system, and it has its intrinsic noise, in this case the projection noise of atoms, then in the absence of entanglement, the best you can do in sensitivity is to achieve the noise which is a factor of 2 greater than the noise of the probe invariance. And this is usually referred to as the standard quantum limit.
Sorry, what means in this case makes a weak measurement?
So the strength of the measurement is defined by the combination of the number of photons you are sending through and the size of the spin. And essentially, in practice, you just choose the number of photons. So if the number of, and now we can refer to the previous slide where I told you that you shouldn't make too strong spontaneous emission, because then you ruin your state. But if your spontaneous emission is very weak, then your measurement is also very weak. So in reality, what you do is you have your certain optical depth, and then you choose the duration of the probe pulse so that the spontaneous emission is exactly optimal, and you get to your golden limit. A bit more physics now from the atomic perspective. Again, you send light through, and the physical origin of this quantum standard quantum limit is in the noise that you write on the atoms because of the fluctuation of light. And so what happens here is that, see, why is this happening? What is meant here is the random disturbance on the energy levels which is caused by quantum fluctuation of light. So light goes through, and even if it's off-resonant, it causes Stark effect. So light is an electromagnetic wave, it changes the energy of the state, and if light has quantum fluctuations, then those quantum fluctuations are mapped on the quantum fluctuations of the energy, and that basically means that you have random phase shift between those That's noise that is imposed by quantum fluctuations of light on the quantum state of atoms. So you can model it in this way, and if it's a signal, then it's just a well-described rotation, and if it's noise, then it's just essentially random. Okay, so can we see it in the experiment? Yes, we can. And what you see in the experiment is the following. Again, you have the atomic ensemble, you have linearly polarized probe with its quantum fluctuations, and you put it in the magnetic field. In the lab frame, the Z projection of the spin is oscillating like that, right? It's oscillating, and the oscillations can be written as the rotating frame Jz times cosine of the oscillation frequency, and similar to Jy. And now you're measuring. And what you measure is written here now in canonical variables. So short noise of light, back action, and now I write the back action in terms of the parameter called comparativity, which is essentially proportional to the optical depth. And the frequency response, the susceptibility of your atomic resonance, and if your atomic resonance is a Lorentzian function, then it's just the susceptibility corresponding to the Lorentzian profile. And you can take this signal, you can electronically split it into cosine and sine oscillations, no problem. Now you will be seeing the noise in this component and the noise in this component. And what you see is proportional to Jz in the rotating frame and Jy in the rotating frame, plus the back action noise. And that's the result of one of the measurements, and this is what has been one of the holy grails. So in this case, the frequency of the Faraday rotation is about 1.5 megahertz. Sorry if you can see those numbers, but it's about 1.5 megahertz. So you tune the magnetic field to 1.5 megahertz, and at this frequency, with our experiment, typically everything is quantum noise limited, because the laser noise at this frequency is very low, close to the shot noise, and at 1.5 megahertz, stray magnetic fields and whatnot are very weak. So with reasonable magnetic shielding, you can get to the quantum limit. And what you see here is that this signal is completely dominated by the quantum back action. How we measure it, that's another story, but we're sure. Whereas this curve would be the almost ground state noise of the spin. That is the projection noise of the spin. So, are we in the optimal regime for magnetometry here? I don't want to stress you, but I will. So remember, I told you that if you want to be in the optimal regime, then the back action should be of the order of the intrinsic noise of the atoms. And it's not. The back action is several times higher than the intrinsic noise of the atoms. So if we would like to use this measurement for magnetometry, then we actually want to reduce the interaction strength so that this thing goes down approximately to here. And then we get the best sensitivity. But because I'm going to tell you about entanglement enhanced measurement, there we want to be completely dominated by the quantum back action. And that's the beginning of the story. Okay, so before we go to the measurement supported by the entanglement, and the generic name of this next chapter will be measurements in the negative mass reference frame. Before we go there, I will just sum up a few.
Sorry.
No worries. I know, yeah, that happens to me. The most exciting thing was that we were demonstrating the quantum cryptography. And that was, I think we were like the third in the world in 1998 to demonstrate quantum cryptography. So it was in a big auditorium at the University of Aarhus in Denmark where I worked. And the people were in the lab, and I was in the auditorium presenting it to the colleagues in the press. And I had to have my phone on to communicate with the lab. And in the middle of all this business, my mom called. Okay, so back to our business, non-trivial problems again. So quantum noise of the initial state of atoms, clear. Quantum measurement changes the state by imposing the back action of the meter, that is light, clear, we talked about. And the meter of light has its own quantum noise. So three main components of the noise. This is one of the incarnations of actually the real measurement. So you see we have significant magnetic insulation, like triple layer magnetic shield, and the the sensor, which is this glass cell filled with atoms, is inside, and it's in the magnetic field, and there are two magnetic fields, right? So there should be the bias magnetic field, which is along the direction like that, and the RF field, which, as we agreed, should be orthogonal to it. So the RF field in this case is produced by those two coils, and this is what we're trying to measure. As a result of this double resonance, so to say, we have certain excitations generated, because if this, so we're looking at the Bloch sphere from the top. Remember, I discussed that, if all the atoms are in the upper state, then on the Bloch sphere you have the vector like that, and we're looking at it from the top, and this is our quantum noise. And what happens when you generate some excitations, for example, because you're applying an RF field, then the Bloch vector is shifted, and this is the shift that you want to measure. So you want to measure the shift, and this is the noise, which is your problem. So this is one of the examples of the cells that we're using. I will talk a little bit more about it in a minute, but essentially what you need to realize so far is that there is a certain channel filled with atoms, and light goes through like that and interacts with those atoms. Those atoms are running around like crazy at 200 meters per second, because this is room temperature gas. But the point is that we need to fulfill a few conditions if we want to have quantum interaction, long-lived, of this light with those atoms. So first, we should have interaction without which atom information, so to say. And this is accomplished by basically two measures. One is that the interaction should last, light, essentially pulse, should last longer than it takes atoms to move around like that, so that all the motion is basically averaged. But if this is like a few millimeters cross-section, then it actually takes just a microsecond for an atom moving in 200 meters per second to cross. So your measurement should just be a little longer than a few microseconds, and you'll find it's not that slow. Another thing is that generally if atoms bang into the glass wall, their spin state is completely randomized. So this is just a killer. If that would be the case, then we could only measure anything meaningful on the time scale of a microsecond, but that's no fun. So the cell is coated from inside with some special alkane coating. In the kitchen language, it's also called paraffin. And this is the technique which is like 50 years old. We just happened to bump into this technique a few years ago to realize that for our quantum state processing, this is ideal. So you think of this coating again as applied to all the walls of the cell. Optically, it's transparent. And again, we think about it as like long spaghetti molecules. And cesium atoms go into this spaghetti on the wall, bounce around for a little while, and come out. And because of the black magic of those spaghetti things, atoms do not exchange energy with them, and they do not decay here. I can talk much more about it, but that's sort of the basic picture. And the lifetime of the spin state, depending on the quality of the coating and depending on the size of the cell, can be anywhere from milliseconds even to a second at room temperature. So you have a macroscopic quantum system containing 10 to the 10, 10 to the 12 atoms, whose quantum state can survive for about a second in the best case scenario, which is pretty amazing. So, because all atoms are oriented in one direction by optical pumping, and because our interaction is insensitive to the position of the atoms, it's averaged out, I can think of it as a large macroscopic spin. In this case, again, 10 to the 10 of those spins. I can draw 10 to the 10, so it's just 5. Those are the beautiful cells that are made by this wonderful gentleman, and it's really fantastic system. So a little bit closer, zooming in. So what we see here is the cross-section of the cell. Light goes through. This is the channel where light propagates. And you should have small losses here and small losses here. And there is a cesium droplet sitting somewhere there. And cesium actually is a wonderful metal. It basically melts in Californian sun because the melting temperature is like 37 degrees. It doesn't melt in Denmark, but it still produces significant vapor pressure. And so this vapor fills out everything here, and atoms go in and out through this channel, but the channel is very small, so for any relevant measurement time, you can consider that you have the same set of atoms just running around here like that. And again, it can be 10 to the 8, it can be 10 to the 10 atoms, and they are all the same as far as the interaction is concerned, and they have the spin lifetime of a fraction of a second. yeah, this is something about those coatings, so we did some significant research about it, and we found that for different types of coatings you can have different lifetimes. So this one is apparently better because it has a longer lifetime, and this is in seconds, so life is good. Yeah, that's the kind of radio oscillations in the magnetic field which allow us to measure the coherence time. Okay, so let's summarize a little bit what I told you so far and what I didn't tell you about, but you can read about it further. So we discussed collective citations and canonical variables for ensembles of polarized atoms and spins. We discussed the basic interactions. We focused on the quantum non-demolition interaction. There are also other types of interactions which we didn't have time to discuss. And in a minute I will tell you about the quantum limited and entanglement magnetometry with this pretty impressive sensitivity, I would say, for a room temperature atomic sensor. And those two subjects will take another couple of lectures, so maybe next time. Okay? So now we need to switch gears and go to the second part of the presentation. Sorry for disturbing you. Yes, so all that so far was essentially old news. So now let's talk about the more recent news, and this is called quantum mechanics in the quantum reference frame, and I will talk about magnetometry using this principle of quantum reference frame. Then I will talk about the measurement of motion, real motion, using this negative mass reference frame. And finally, I will tell you a little bit, maybe this afternoon, about the applications of this wonderful business. Okay, so again, refreshing. What are the quantum limits of measurement for motion and for fields? So we have a certain canonical variable in the lab frame. It can be a mechanical oscillator. This is my first slide, you remember. It can be mechanical oscillator, it can be magnetic oscillator, it can be light, whatever. The point is that you cannot measure simultaneous flexibility. So what's the best you can do? You can do two things. One is you can try to measure X and put all the back action into P, and in this way you will generate a squeezed state of your oscillator and can use it for sensitive measurements. And the other thing is that you can do the minimally invasive measurement. You will measure both sine and cosine quadratures, but only at the step quantum limit sensitivity, which is the square root of 2 times the ground state uncertainty. Yes, so that's why. Measurement of X imposes uncertainty and P, the other way around, quantum back action of measurement. You should be able to lecture all that yourself. Right? And this is, again, a small cartoon. Essentially, we have the lab frame X, which is oscillating. And you are measuring the projection on this direction in the lab frame. But the point is that they oscillate. So when you measure X, you put the back action in P. Now, the next moment you are measuring P and putting the back action on X. And the more you measure, the more you put the back action. And this is precisely this peak that I've shown you from the experiment. It's the back action noise of the atomic spin, or similarly to the motion of an oscillator. And so my message is that despite all these obvious limitations, one can measure arbitrary small perturbations in both position and momentum simultaneously, but you need to choose the correct reference frame. So let's see how it works. We call them trajectories without quantum uncertainties. Those are the papers in the inverse chronological order that discuss this business. In fact, the very first paper was in 2001, but we just didn't call it negative mass reference frame, so it didn't have as much splash. Carl Case and his co-workers, they developed in 2010 a rather complete theory of such a measurement, and they call it quantum mechanics free subspaces. The title that I don't like, because I think this is quantum physics in its best. But indeed, you can make measurements which are not restricted by the uncertainty principle. So you need to make a measurement of the trajectory. What is the trajectory? For example, it's the behavior of the atomic spin under the influence of the external magnetic field. That's a trajectory. Or the trajectory is the motion of the mechanical oscillator under the influence of external forces. Also a trajectory. So you need to define this trajectory in a negative mass reference frame. And then this is what we usually in phase space would call classical trajectory. The system undergoes some change, like it goes from point A to point B. This is what a typical quantum trajectory would look like. If we know the position initially of the particle, then for sure we don't know how this wave packet will propagate, unless we do tricks. And so what we want to achieve is to have the same precision on the quantum trajectory that we usually have in the classical. And this apparently gives you a big edge in terms of measurements of fields, forces, and whatnot. So let's go back to the giants. And the giants will tell us that there is this standard quantum limit, and the Heisenberg microscope is a very famous example. So we want to observe the position of a particle. What does it mean to observe? Well, that means to, for example, shine light on it, scatter this light from this particle, and detect the light. And then you know where the particle is. Well, to be more precise, you know where the particle was. Because when you scatter a photon from the particle, you also give a kick to this particle. And if you play pool or billiard, as you wish, then if you are good, you can predict this trajectory. But for quantum balls, you cannot. Because we know that if we focus light very tightly so that we know where the particle was, then due to the wave-particle duality of light, the wave packet of the photon will be very much unknown. So that essentially means that you don't know in which direction this photon is propagating after this measurement. And if you don't know the momentum of the photon, then you certainly don't know the momentum of the atom, because the total momentum is conserved. This is, if you wish, the most hand-waving explanation of the uncertainty principle between the position and the momentum. if you want to put it in more strict terms, then you say, okay, this is the position of my particle as a function of time, which is the initial position plus momentum divided by the mass, which is velocity times time. So that's what? In what grade in Brazil do they discuss kinematics of motion? Have you guys gone to school? No, I'm just interested because in different countries it's different.
First year high school.
First year high school. That's okay. All right, so everybody went through high school?
Yeah.
Somebody hasn't gone through the high school? Okay, so now what they didn't tell you in high school, or at least not to all of you, is that the delta x times delta p is greater than h bar over 2. So x and p cannot be measured and known simultaneously, and the best you can do if you want to estimate the delta x, this one, is to minimize the uncertainty of this sum. And so it will be the uncertainty of x, and then from the uncertainty principle, you express the uncertainty of delta p. So delta p is h bar over 2 delta x. You put it here. It's squared because this is the variance. And what you get is what you deserve, and that is this one grows with delta x, this one goes down with delta x, and there is a minimum, which is easy to calculate, right? So x plus a over x, you minimize this sum, right? How do you minimize this sum? You take the derivative and you put it to 0. Okay? In case you haven't had enough. I'm sure you have. Anyways, so we make the sum, and what we get is h bar times t over x. For a free particle, this is the standard quantum limit. And t is the time of the measurement, if you will. Right. So, if we want to make the trajectory, if we want to trace the trajectory of motion beyond this quantum limit, then we need to do the following. We need to define the trajectory relative to a quantum reference frame. Indeed, when we talk about trajectory, we always mean that it's in some reference frame. And typically, my trajectory is in your reference frame. But in quantum physics, why don't we introduce a quantum reference frame, another object with respect to which we make the measurement of the first one. This reference system should have an effective negative mass, and we will look at it in a minute. You create an entangled state of the reference system and the probe system. And that's it. You make a measurement with respect to this reference frame. So let's look at how this futuristic scenario works. Again, I remind you about this EPR type of entanglement that we already discussed yesterday. This is the key component. So it's the system where the x and p of the two systems can be correlated in such a way that you know exactly the sum of p's and the difference of x's. All right. So in this kind of phasor diagram, if we have a entangled state between the system of interest and the reference system, then the difference of x's and the sum of p's is very well defined, and you can always put it to 0. Okay, so it's like that. And now let's do our favorite kinematics once again. But now for the difference between the position of our system and the position of the reference frame is a function of time. This is the initial difference at time 0. I put the mass to be 1 to make life easier, and then it's x dot, which is p, minus x 0 dot, which is p naught, times t. Again, kinematics. The difference of axes plus the difference of momentum times t. Is it good? Not really, because the difference of the positions and the difference of the momentum, they don't commute. Now you should immediately already see what we need. We needed to change this sign, because then it will be the difference of positions and the sum of the momentum. And those two variables can be measured simultaneously with arbitrary accuracy. So, well, this is what we need. We need somehow to come up with a reference system which has the effective negative mass. And then, in this reference frame, we can have the trajectory which is defined as good as it gets. Very similar discussion can be taken for two oscillators. So for two oscillators, this is the oscillator of interest, this is the reference oscillator. You take the difference of x's times cosine and the sum of p's times sine. And here I already assumed that the frequency of this reference oscillator is negative. So I will interchangeably use negative frequency and negative mass. You will see that it's the same thing for this kind of approach. And so if now I have the APR state, then this can go to 0, this can go to 0, and I can make this measurement with arbitrary system. Something wrong. So this reference oscillator, for an oscillator you have omega square equals to k over m, elasticity over the mass. This is also, if not high school, but at least the mechanics in college, right? So for my reference oscillator, all three of those are negative. Let's see how it works. In fact, you have seen this already before. It's an atomic spin in magnetic field, and let's show that actually it can work as a negative mass oscillator. So we polarize all our atoms in the upper state. They have the quantum uncertainty of this state. If we zoom into this North Pole, then we can normalize the Jx, Jy projections into x and p. So if we look closely into this area, it's like flat surface with x and p minimal uncertainty. Now, suppose we generate some quantum state which is different from the ground state. But what happens is that apparently the energy of this new state is lower than the energy of the initial state, isn't it? Of course it's lower. I flipped one particle spin. So in fact, if I don't know which particle flipped the spin, and we discussed it already, right? So all interesting quantum states in this approach should be generated collectively so that you don't know which particle flipped the spin. And in fact, it will be like a Fock state, like the first excited state of this oscillator. And that's what it is. Now, is this state larger than that one? Yes, it is larger. If you take larger in the sense of like the spread on the blosphere, and now we remember, hey, but this is a sphere, this is not exactly a flat space. So the larger state is closer to the southern pole, which means that we put an energy in this oscillator and we put an excitation in this oscillator and we reduced its energy. And that's the negative mass, negative frequency oscillator, as simple as that. Okay? So, depending on whether you initialize your spin oscillator in the state where all atoms are in the upper state, or you initialize it in the state where all spins are in the lower state, you can have either negative mass or positive mass oscillator. Yeah, that's the mathematical description of this superposition where one spin is flipped but you don't know which one. And then you put it in a magnetic field and you have an oscillator which has an effective negative mass because the more excitations you put in, the lower is its energy. Okay, so you've seen this, in fact, already. I just added for completeness. For a single oscillator, we want to be in the quantum back-action dominating regime. And now let's look at the combination of the two oscillators, one in the positive regime, one in the negative mass regime, and the application will be this entanglement-assisted magnetometry with extremely high sensitivity. So, two magnetic sensors with opposite spin orientations. One of them is the negative mass, one in the positive mass, and you make a joint measurement. So that's what it is. One oscillator, another oscillator. Magnetic fields are the same. The orientations of the spin are opposite. What? Yes. So this spin is oriented like that and oscillating like this, and this spin is oriented like that and oscillating like this. They oscillate synchronously because the magnetic fields are the same. And what you measure is the quadrature of light that goes through as before. You have the shot noise of light as before. You have now the signal from both spins. So the Z projection of this spin and the Z projection of this spin. And you have the back action. And the point is that something here got lost. I'm sorry. And that's the important thing that got lost, because this is the back action on the first oscillator. And I'm sorry, but you have to imagine that the second back action on the second oscillator has the same shape, but an opposite side of the susceptibility. How did it happen? I
It's
don't
actually on the left side.
It broke the line.
This is what I call attentive audience. Thank you very much. All right, so good points. Yes, everything else is forgiven. So now, once again, just I wanted across this one too. So again, this is the back action from one ensemble on light. This is the back action from the other ensemble on light. It is driven by the same noise of light. You don't want to lose any light in between, because otherwise you will not get the right cancellation. And you have to choose the susceptibility of one of them to be opposite to the other one, and that is achieved when you have the opposite orientation of the spins. And so this one cancels out, this one cancels out, and you get only that one. And if you have strong enough comparativity, or in other words, high enough optical depth, then this term will be dominating over shot noise of light, and that means that you can measure the sum of the two spins in the rotating frame as good as it gets. And if you can measure the sum as good as it gets in the rotating frame, that means that you can measure the sum of Z projections and the Y projections. So you know the mutual orientation of those spins in principle with arbitrary cues. So for one of them, it will be like that. Hey, keep going. So this is the back action on one of them, which gives you extra noise. And the same light goes through, and this is the back action on the other one, and it gives it extra noise. But the point is that those two extra noise sources are the same noise sources. And so your spins, they still remain parallel, because the hit that they got from the back action is equal and opposite side. So we're looking from the top, like our spin, I think. Okay, so we send light through, and we can create a state where the two spins are exactly anti-parallel. We don't know the direction of each of them within the back action uncertainty, but we don't need to. So, how do we use it? Well, we have two of those ensembles, oppositely oriented. Each of them has an uncertainty, but we can create the spin state where they are more parallel than the standard quantum limit, because they're entangled. And so now we can make a measurement of the field in the rotating frame with very high accuracy. So I don't have much time to discuss it, but that's essentially how you connect the amplitude of the RF field you want to measure to the shift in the spin direction that you want to observe. That's the experimental incarnation from 10 years ago. You send light through the two ensembles, and they have opposite spin orientations. You create an entanglement, and you apply the RF field, and you make the measurement. So in reality, they entangle, we run entangle, send the RF field that you want to measure, and then you read out. And by means of entanglement, we can generate this two-mode entangled state of two macroscopic spins, where this is not zero. We would love it to be zero, but it's not zero. But it's definitely less than the quantum limit. And by means of that, we can achieve the improvement of the measurement of the magnetic field by 30%. So this is the sensitivity that we obtained some years ago, which is in the sub-femtotesla range per hertz. I don't know. Okay, shall we maybe stop here? Alright, because the next and the last part will be implementation of all this jazz to the motion of a mechanical object. So far we talked about the entanglement of a spin with respect to another spin. So this can be used for tracing the magnetic field with arbitrary accuracy. And now, instead of the positive, nice quote-unquote magnetic oscillator, let's take the regular oscillator, just mechanical membrane oscillating, measure it together with the magnetic negative mass oscillator, and see that we can trace the motion with the accuracy which is higher than this time quantum. Okay? Thank you.
Questions?
Thank you for the talk. So you said that when you have your spin ensemble, it's good to have one spin that is not in the direction, so we can create this system that has like lower energy, and therefore we have this kind of negative mass. But is there an optimal amount, like a percentage of the amount of spins that you have that can give you a better result, or just one is enough?
Okay, so the question refers to this business. Sorry, yes. So this was an example to demonstrate that an excitation in the system acts as if the system has a negative mass. If, for example, I generate a two-mode entangled state between those two spins, then you will be able to write it down as the usual two-mode squeeze state, which will be, shall I write it here? So the two-mode entangled state will be something like 0, 0 with some coefficient, plus 1, 1 with some coefficient, plus 2, 2, and so on, right? So this is the mathematics of the two-mode entangled state, two-mode squeeze state, if you will. So that essentially means that the two-mode squeeze state, two-mode entangled state, is a superposition of different numbers of interactions. Those coefficients depend on the degree of entanglement. The higher they are, the more terms you have. But the point is that there are always the same number of interactions. So this was just an illustration, whereas, yeah.
So for me it seems a bit unintuitive that something in nature can have a negative mass or negative frequency. So just to understand, there was like some physicist who saw that he can model this spin down, so in your ensemble, with just setting mass to 0, to minus m. Is this correct? Or like how did people approach this problem?
Yes, and you observe one of those physicists just in front of you.
I don't know.
So I'm live and kicking.
But didn't you, like, because for me it would feel like wrong, like the first grasp would be like I do something wrong, but then you just saw, hey, in experiments, this maybe like the things that I see, these add up in the end, so it's actually okay to do it.
I see, so the question is more like, what is the evolution of thought?
Yeah.
in
Yes.
this business? That's a good question. So, the story went in the following way. Back in 2000, we were thinking of how to do this magnetometry, AC magnetometry, and it just occurred to me that we can do it with oppositely oriented spins, and then the back action will be negative, it will cancel out, we can do it. So we published the paper. And then there was no notion of negative mass in the paper, but it essentially demonstrated the principle. And then a few years later, in 2008, my good friends Peter Zoller and Clemens Kammerer, we talked about it, and they say, oh look, we can call it a negative mass oscillator. I said, sure, let's call it a negative mass oscillator. And then this was the first time when this notion was introduced to such systems. And then Carl Gates and co-workers, a couple of years later, they kind of reinvented it in a more general perspective, and then it became kind of the mainstream, so to say. Thanks for the question.
Okay, thank you.
It's interesting. In fact, I have to mention that the giants like Aronov and others, they talked, and Glauber, they talked about measurements in quantum reference frames earlier than us, but it was a different context and no negativeness there.
More questions? Okay, so if there's no more questions, let's thank Professor Polzik.